First of all, I'd like to thank organizers for giving me the chance to be here. The title of my talk is Hybrid Quantum Information Processing. My hybrid means my information is encoded in amplitude phase of electromagnetic field, but it is cubic. And my subtitle is a way for large-scale optical quantum information process. These are collaborators. Here is my group at the University of Tokyo, and here are senior collaborators, including Jeremy O'Brien, Dylan Mala, and Alberto Poli. We are working on quantum teleportation chip for continuous variable, like this. It is fabricated by NTT. The reason why we are working on this type of chip is that by using this technology, we can make universal quantum information processing forever. It is actually teleportation from this node to this node and sequentially. And changing this measurement basis, we can change the operation. And this methodology can be extended into 2D cluster state, like this. Importantly, only with 4 squeeze vacuum and 5 beam splitters and only 2 delay lines, we can create this gigantic continuous variable cluster state. This is deterministic. This size is 10 to 6 nodes, and this is infinity. And we can make measurement and feed forward, and we can make universal quantum information processing with this one. So this is large-scale optical quantum information processing. And hybrid quantum information processing is for fault tolerance. As a first step, we created continuous variable entanglement on a chip. That is collaboration with Alberto and Jeremy. Here is a chip, a very small one compared to this 10 yen Japanese coin. And we created entanglement on a chip and verified the entanglement on the chip. And by using that technology, we made a teleportation chip. This is the first version. And we did teleportation experiment. Here is input coherent state, and this is quantum teleportation output. And the fidelity was 0.65. It is a little bit better than classical limit, but a little bit lower than no cloning limit. So now we are making, unfortunately, we cannot see the circuit, but we are making a new chip. And we will try to make entanglement swapping in a chip. And we can get more than 2/3 of the fidelity. That is no cloning limit. In that case, we can teleport non-Gaussians with the negativity of the Wigner function. In this talk, I will talk about quantum information processing. And there are 2 types of encoding of quantum information. One is, of course, qubit and digital encoding. Another one is continuous variable. And this is analog encoding. Information is encoded in complex amplitude or amplitude and phase of electromagnetic fields. And there are 2 types of qubits. One is stationary qubit, like spin ion atom or artificial atom, superconducting qubit, state like this. And another one is called flying qubit. It is photon. The big difference of flying qubit is we need real quantum circuit. In this stationary qubit, you don't have to have real quantum circuit. But for flying qubit, we need a real circuit. That is a big difference. And of course, everybody loves qubit because we can make high fidelity operation. It is exactly the same as digital TV compared to analog TV. There is a caveat. We should know the difference between physical qubit and logical qubit for quantum error correction. Physical qubit are, of course, superposition of horizontal and vertical polarization of single photon, or up spin and down spin, and ground state and excited state. These are physical qubits. But only with physical qubits, you cannot make fault-tolerant quantum information processing. For fault-tolerance, we need logical qubit for quantum error correction. This is an example of logical qubit for quantum error correction. It is called 9-qubit code. That means one logical qubit for quantum error correction needs 9 physical qubits. That is world record of superconducting qubits. In any case, we need many physical qubits for fault-tolerant quantum information processing. In that situation, photon is the best qubit because it has perfect uniformity and there is no crosstalk, and it can survive in room temperature. And this is very important. We can make time domain multiplexing. That is because flying qubit. For example, if we can use 5 pulses or 9-wave packets, we can make logical qubit with 1 optical beam. This is time domain multiplexing. As you know, there are 2 types of quantum information processing, and most of your side are working on quantum circuit model. So in this model, you need quantum gates, and for qubit, it was proposed by Richard Feynman around 1980. And for continuous variable, quantum circuit model proposed by Seth Lloyd and Sam Brownstein around 1999. And there is another type of quantum information processing model, that is measurement-based model, or one-way quantum computing. For one-way quantum computing, first we prepare a large-scale entangled state called cluster state, and make measurement and feed forward. For qubit, Rausendorf and Briegel proposed one-way quantum computing in 2001. And in this case, these nodes are superposition of 0 and 1. And all nodes are entangled. So in some sense, this is entangled state with all possible states. And similarly, for continuous variable, Nick Nikuchi proposed continuous variable cluster state and one-way quantum computation. And in that case, these nodes correspond to superposition of all possible states. And again, entangled like this, 2D in 2D. And naively speaking, this cluster state corresponds to a superposition of all possible quantum information processing patterns. So by using measurement, you can select one of them. And that is a mechanism of one-way quantum computing. And in other words, depending on the measurement result, we may fit forward. So in that sense, this is sequential teleportation. And if you change the measurement basis, you can change the operation. So it is pretty much teleportation. And this cluster state is a stabilizer state, which means error correction friendly. And in any case, for quantum error correction, you have to make syndrome measurement. So you have to make a measurement. So it is, even in that sense, this computing is error correction friendly. And it is extremely powerful for flying qubits. If you want to make large-scale quantum information processing with flying qubits, you need very large scale optical setup. And also, no flexibility of the setup. I mean, if you change the operation, you have to change the circuit. I think that is very big problem. By using one-way quantum computing with time domain multiplexing, we can solve these problems. By using this time domain multiplexing, we can create ultra large scale continuous variable cluster state. For example, 4 years ago, we created 10,000 wave packet continuous variable cluster state. It is 1 diesel. And then last year, we succeeded in 1 million. And actually, it is unlimited. So mechanism is very simple. Squeeze light, that is superposition of all possible state and making entanglement like this. And one arm is delayed by one wave packet, and then recombine here and creating cluster state. And we make measurement one by one, like this. And we check entanglement forever. So we can create this gigantic time domain multiplexing with continuous variable speed. It is deterministic. And we can make large-scale quantum information processing only by this setting. I mean, only 2 speed vacuum and 2 beam splitter and 1 delay line. And we can do quantum information processing forever. It is 1 diesel. And it is programmable. When we change the measurement basis, we can change the operation. We can create a large-scale continuous variable cluster state with time domain multiplexing. But we need qubit encoding for high fidelity quantum information processing. That's why we need hybridization. So we encode qubits. This is a very simple example of qubit superposition of 0 and 1 photon. And like this, quantum information is encoded in amplitude and phase. Like this. And continuous variable processing, we can make fault-tolerant quantum information processing. I want to explain the mechanism of one-way quantum computing. Here is the essence of quantum teleportation. This is input, and here is ancillary input. We make entanglement between them, and we make measurement here. Because of entanglement between them, making measurement make some change here, and then depending on the measurement result, we make some operation here, and input state appeared here. This is teleportation. And one-way quantum computing, something like this. For the qubit, we use superposition of 0 and 1. And for continuous variable, it is superposition of all possible states. The approximation is squeeze vacuum. And here, we make entanglement. And depending on the operation, we change the measurement basis here, and we can make operation here for arbitrary input. In the case of I, U equals I, that is actually teleportation. And we can cascade this one like this. So in that case, we can make 3 operations like this, and it is called cluster state. And we are creating this continuous variable cluster state. And we can create the cluster state deterministically by using squeeze states. Optical parametric process, by using optical parametric process, we can create squeeze vacuum. And in that case, signal and hydra are entangled like this or like this. And in the case of wavelengths of signal and hydra are the same, it is called squeeze state or squeeze vacuum. And by using squeeze vacuum, by using 2 squeeze vacuum and beam splitter, we can create EPR beam. And by using 3 of them, we can create 3-mode clusters. And then by using time domain multiplexing, we can create forever. And we can make large-scale quantum computing. This is teleportation from here to here. And this methodology can be extended to 2D. By using 4 squeeze vacuum and 5 beam splitters and 2 delay line, we can create this type of cluster state. More precisely, that is a spiral of the state, and these are equivalent. And this dimension is determined by the laser coherence time, and this dimension is forever. So it is pretty much scalable. There is a big advantage of hybrid quantum information processing. The operation bandwidth is determined by squeezing bandwidth. And we are now coming 100 megahertz, and hopefully we can go to 1 gigahertz soon. And in that case, we can handle photons with 100 megahertz and 1 gigahertz, which correspond to 10 nanosecond time duration or 1 nanosecond time duration wave packet. And if laser coherence time is 1 millisecond, we can make time domain multiplexing by 10 to 6. And we can make batch processing. And importantly, the operation time is unlimited. That is because we make a measurement within laser coherence time. So we can continue the quantum information processing forever. On top of that, each web packet can contain more than one photon. I mean, we can add a degree of freedom of photon number. That is extremely important for quantum error correction. In some sense, time domain 2D plus photon number dimension, so 3D clusters. And logical qubits for quantum error detection and correction with degrees of freedom of wave packet and photon number can be created with this scheme. This is example. This is very simple. Dual rail qubit, two-way packets and single photon. 0, 1, and 1, 1, 0. That is error detection code. And bosonic code, this is error correction code. In that case, two-way packets and 4 photons. It is error correction code for photon losses. And it is called noon code. 4-way packets and 4 photons. And we already used these qubits. For example, we already teleported this time being qubit like this. And also we teleported the primitive of bosonic code or noon code. Actually, this is Q trip. 2-way packets and 2 photons. And we created this type of logical qubit and teleport. We made deterministic teleportation. I'd like to move on to another topic, that is universality of this type of operation. At the moment, we are just using homodyne detection, just changing the local oscillator phase. In that case, we can achieve universal Gaussian operation. For true universality, we need one nonlinear measurement. For that purpose, we use the methodology to create cubic phase. It is a continuous variable version of pi over 8, so universality. This methodology looks simple. I mean, this is arbitrary input, and here is ancillary squeeze vacuum, and this is continuous variable version of magic state called cubic phase state, and only 2 beam splitters. So for optics, the setup looks very simple. But for this feed-forward electronics, it looks very nasty. Here we make homodyne measurement, and we get x. And by using this x, we calculate this arctangent. And by using this theta, we make adaptive homodyne measurement. And we get that value. And then we make calculation and this value and make this place. It is pretty much a nonlinear feed-forward. But we can create cubic phase operation like this. And the important message here is that we can create optical nonlinearity can be created with classical nonlinear feed-forward or classical electrical circuit. Optical nonlinearity can be created by using classical nonlinear feed-forward. non-classicality can be created with non-classical ancillary inputs. So this is very important message. And actually, this is nonlinear measurement, projection onto magic state. And we are building this nonlinear feed-forward. So again, this is a whole circuit, but we are modifying this one. And here is a dummy measurement result, just sine wave. And here is nonlinear feed-forward, calculation of arc tangent and adaptive homodyne measurement, and calculation of this value and this place. Input-output relation becomes like this. And if we have enough squeezing level, we can neglect these terms. And this is input-output relation. And it depends on this kappa input or dummy measurement result. So if kappa is negative, this type of squeeze, and kappa equals 0, or this type of squeezing, and kappa equals positive, this type of squeezing. So it is dynamic squeezing, depending on this value. And we made that experiment, dynamic squeezing gate, by using analog electronics. But as you know, analog electronics is kind of unstable. So to solve that problem, we ordered this one. That is ultra low latency FPGA board. I mean, we solved the problem by using money. It costs like 0.1 million US dollars. So now we are very close to realize this nonlinear measurement. So it can become universal. Let me summarize my talk. We are now working on this continuous variable teleportation chip. That is because by using this technology, we can make this type of chip. Actually, it is very, very similar to teleportation. This is making entanglement, this is bell measurement and feed-forward. So almost the same. Only difference is feed-forward coming here before this beam splitter. And delay line. That is the only difference from this. And this methodology can be extended to 2D like this. So again, we are working on large-scale optical command information processing with very tiny setup. And for hybrid quantum information, by using hybrid quantum information processing, we will pursue fault tolerance. And in near future, we will make all optical quantum computing. And the clock frequency is more than 1 terahertz, according to Tim Lau's paper. That is my. Thank you for attention.
Questions from the floor? Go right here.
Again, so I'm always asking questions. This was an amazing talk. Thanks very much, Akira. This is something that's always confused me, so I've asked many people in the room this same question. So you need this kind of magic state, in the same way that with discrete variables, you need these magic states for universality.
Yeah.
How many of these operations do you need? Do you need one of these magic states at every clock cycle, or do you need Do you need one for every qubit, or maybe you just need one for the whole? You just need to inject one for the whole task. Is that already something that's known, or?
Most of operation is Gaussian. So, are you familiar with topological quantum computing?
Familiar would be overstating it, but yeah.
Yeah, so
I know the idea.
in that case, braiding corresponds to Clifford operation, right? So that corresponds to Gaussian operation. So most of operation is Clifford operation, and sometimes you need non-Clifford, that is non-Gaussian. So that is exactly the same as topological quantum information processing. So it depends on the case. Sometimes you need many non-Gaussian operations, but I don't think so.
So I wanted to ask, you mentioned when you were talking about the nonlinear measurements, you said if you had enough squeezing, what is the relationship between the amount of squeezing that you need to start with and obtaining, let's say, fault tolerance, or in the latter example, the nonlinear measurement?
Yeah. There is a theoretical calculation by Nick Menikuchi. If we can prepare GKP qubit, that is kind of surface cool. And if we have 20 dB of squeezing, the whole process becomes fault tolerant. But as you know, the world record of squeezing is only 15 dB. So we need 20 dB, so it is a little bit too much. But if even with 15 dB of squeezing, we can make this type of error rate with 10 photons GKP. So now we are making research on how to make fault tolerance with 10 dB of squeeze and up to 6 photons. I think it's feasible.
Okay, I have some more questions, but maybe I'll ask you later. Let's thank Akira.